Welcome to a lesson with Dr. Powell. Let's take another look at this example where we were finding, we were determining if a certain critical point was a maximum or minimum. This is an introductory example that we're working through. And just to kind of review what we did, we learned how to take the second derivative. And we had this intuitive argument to ensure what we needed um, for the in looking at the second derivative to determine what we could discover about being a maximum or a minimum or neither. All right, now let's take a look at this argument a little bit more. Um, what we're going to do is we're going to look at the point. So we had an intuitive argument right there, and it honestly could be made rigorous. It actually works well, but this is just another take on it. Suppose that we had our point where now at this point, remember what we had. We knew that the derivative here at this point, 0, 1, 0, was actually equal to the 0 matrix. All right, so it was 0 at that point. And let's suppose that we go to a point change of x, 1 plus change of y, change of z. We're just adding change of x, change of y, change of z to that first point right there. And we're coming here. Now let's just consider any path that we can take from that critical point to there. That path will be like a function from a parameter t, our position on the path, to into space, R3, okay? Because that's kind of what we're looking at. The input is in XYZ coordinates anyhow, so that's really what we're looking at. So what we're going to do is we're going to look at a path that goes from there to there, and we're going to compose it with f. So f of p, so we can actually change our whole situation to a single variable case. So we input one thing and we output another thing. All right. All right. Now, as we do this, realize what the derivative of p is. Okay, of the path. Now this is the path that we chose, and we're thinking of change of x, change of y, change of z. At least for the time being, we're gonna think of them as being constants. Just fix them for now. So we're going from here to a particular point, and letting t be the variable. So concerning the derivative right here, dp, notice what we're doing is we're just taking a derivative of all of these we're just looking at the change of this with respect to the single variable that we have going into it, which is t. I mean, this is a function that has like 3 different outputs, but it has one variable. So it's like you're taking a derivative of each output one at a time. So this one, just change of x, this one, change of y, this one, change of z. Okay, so we're going to think about the derivative of the path as simply being just the derivatives of each component in turn. Okay, just thinking of it that way. So we have a derivative for each output, because each output is like a function, right? And so, anyways, we're going to think of it that way. All right. So as we go, we're going to introduce a few ideas, but hopefully intuition will serve us. So here we have we want to take the derivative of f with respect to t. That's like taking the derivative of this composition. Composition means chain rule, right? So chain rule is like multiplication. Here it'll be like multiplication of matrices. So the derivative with respect to f times the derivative with respect to p, but where we've plugged in p, we have a variable substitution here. So we'll just remember that x, y, z have like these substitutions in here, but we'll just write them out this way. This would be like what df would be, and this is what dp is. This is the derivative of p, of the path. That's the derivative of the function. Now, let's take a derivative of that to get a second derivative. Okay. So let's rewrite this. All right. So this matrix product, this is a dot product. We can actually rewrite it this way. It means the same thing. To give us, it'll give us the same dot product output. So we write, so we have this right here, and we take its derivative to get a matrix. This is a constant, right? Because these guys were constant here with respect to t. So we get a constant, but then this, by the chain rule, gives us another because it's the same thing again, right? Derivative of um, this is composed with p, right? Because x, y, z or have p come in, so we have to like multiply by the derivative of p of the path again. So we end up getting this right here, and guess what this is? This is f double prime of t. That's the second derivative with t plugged in. Is that matrix product that we were looking at before? Okay, so now what we're going to do is we're going to think, okay, um, with change of x, change of y, and change of z right here in this location, this is the same thing as saying that t is 1. So this is like f of 1 where t is equal to 1. And what we're going to do is we're going to think of that as being equal to f of 0 plus how much f changes from 0 to 1, right? Now, what's the change of f from 0 to 1? That's f of 1 minus f of 0, which is the same thing as this integral of its derivative from 0 to 1. Now you can do the same trick with its derivative. We can rewrite that as what its derivative is at 0 plus how much it changes up till h, right? So this is like f of h, f prime of h minus f of 0. We're using another variable here so that we have bounds being different than our than our inputs here for our axes and our bounds on our axes. So we get this, and we realize in our situation that in our particular situation, all right, so that f of 0, I guess f of 0 doesn't necessarily have to be 0 in this particular case, yet f prime we've assumed to be 0, okay? So this is actually going to be equal to f of 0 plus this amount, okay, right here. And realize, so what is this? This is actually the change of f, all right? The change of f, and when t is 0, that's like saying what f of 0, 1, 0. So what f is at that critical point, right? So what is the change of f past that f value? Now, in this particular case, if we what we'd like is we want if this is all positive, then this would be this would represent a minimum as we move away. If it's negative, it'd be a maximum. Or so let's take a look at how can we ensure that this would always be positive, for instance. Well, if we assume that f double prime is continuous, a continuous function, if we make change of x, change of y, change of z small enough so that things won't change very much, values won't change very much, then if we just ensure that the second derivative is of 0 is positive, okay, then that means that if everything's small enough, then you're not going to get away from being positive because by continuity if you move just a little bit away, which means that that the second derivative with anything plugged in between 0 and 1 is always going to be positive because change of x, change of y, change of z are small. So, I mean, t is just a parameter along this path, but really if you just crunch these down small enough, if you have a point that's where the output is positive, a function that's continuous, if you go anywhere nearby, if you make a small enough circle around it, it's going to be positive as well still. So we're going to use that idea to realize that we can make it small enough so that with this second derivative being positive, it actually makes this whole integration positive, which makes that change of f positive. So that's just a little technical argument, but it works as well. The nice thing about this argument is that we're actually dealing with directly from this point plus a change, and then seeing how that change is positive just right there in that particular case. Then again, as we're looking at this, we can plug in our point. In this example, it was neither positive definite or negative definite, but at this point, but you can kind of see that the second derivative of where t is equal to 0 is actually equal to this calculation right here that we had. It's actually equal to this matrix calculation. So, and so to make sure this is always positive, we're just looking to see if this is positive, is right here is positive definite or negative definite. Thanks for watching.